So our next speaker is Hester Graves. The title of the presentation is "The ABC Conjecture Implies that Only Finitely Many s-Cullen Numbers Are Repunit."
So first, I would like to thank the organizers. This is my 5th time at the Maine Quebec Number Theory Conference, but it is my first time that I am at the conference, yet I am in neither Maine nor Quebec. So I'd like to thank you guys for soldiering on and running this conference in these absurd times. I'd also like to start my talk with another thank you, which is I would like to thank Miss Janice Malloy for allowing me to be able to continue researching. I have a toddler and these are crazy times, and it's only due to her and some heroic measures that I was able to have the time to do this research with my colleague, John Grantham. We both work at IDA-CCS. So on to this, my very first Zoom talk. The ABC conjecture implies that only finitely many Cullen numbers are repunits. Since I had always thought I had to be in the same room as my audience to give a talk, I'm considering all rules are out the window. And one of the rules I was always told is no proofs in talks. People can't follow them. But I am breaking this rule and I am giving you guys not one, but 2 proofs. So the title is "The ABC Conjecture Implies that Only Finitely Many Cullen Numbers Are Repunits." And this is a dense title. It's got 3 terms in it people might not know. They might not know what a Cullen number is, they might not know what a repunit is, and they might not know what the ABC conjecture is. So we are going to start by defining those terms. Oh, come on, there we go. So the sequence C sub n equal to n times 2 to the n plus 1, where n ranges over the positive integers, are the Cullen numbers. And the s-Cullen numbers are numbers of the form n times s to the n plus 1, where s and n are positive integers and s is greater than or equal to 2, because having s equal to 1 would be silly. You may look at these numbers, these definitions, and I think your reaction says a lot about your attitude towards mathematics. Some people would look at these numbers and say, why do we care? And other people would look at these numbers and it is catnip, right? N times 2 to the n plus 1, that is irresistible. To people in the first camp who aren't immediately drawn in by that definition, I can give you a fancy pants reason to care, which is that Hooley cared. And Hooley showed that almost all Cullen numbers are composite, and there is a tempting open problem. It is conjectured, but not proven, that there are infinitely many prime Cullen numbers. Luca, and I apologize, I'm probably mispronouncing this, Stanica showed that there are only finitely many Cullen numbers, which are also Fibonacci numbers. And then Marcus generalized this result to s-Cullen numbers for fixed s. And then keep in mind, Fibonacci numbers are one example of a recurrent sequence. Bilou, Marcus, and Tobey then expanded this to other recurrent sequences. For a fixed s, there are only finitely many s-Cullen numbers that are also in a fixed recurrent sequence. So I have now told you about Cullen numbers. We now move on to repunits. So a repunit is a positive integer n that we can write as b to the q minus 1 divided by b minus 1. That can be rewritten as b to the q minus 1 plus b to the q minus 2 plus all the way down to plus b plus 1. Or we can write it as 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, base b. Therefore, we have repeated the unit in base b, and they are called repunits. Again, we want our integer base to be greater than 1, because otherwise we can write any number, any positive integer this way. And we want our integer exponent to be greater than or equal to 3. Why? If we allow length 1, that's just the number 1. That's boring. If we allow length 2, then any positive integer n greater than 1 can be written as n minus 1 plus 1. And so any positive integer greater than 1 can be written as a rep unit of length 2. That is also boring. So we're telling ourselves we only care about length greater than or equal to 3. So some examples, 11111 is a base 10 rep unit, and 7, which can be written as 4 plus 2 plus 1, which is 111 base 2, is a rep unit base 2. All right, we have talked about rep units. Now I need to tell you guys what the ABC conjecture is. However, the ABC conjecture requires you to know what a radical is. So the radical of a positive integer n is the product of all the primes that divide n. So if n is the product of primes p sub 1 to the ai, where the p sub i's, where the p sub i's are different, then the radical of n is the product of the pi's. So for example, the radical of 90, which is 2 times 3 squared times 5, is 30 because that's 2 times 3 times 5. And if I can go on a little tangent here, if you'll forgive me this, when I was young, Fermat's last theorem was an open problem. Anyone could understand it, and it was super exciting that there was this easy to state problem for children that no one knew how to do. And I think that if we look at the ABC conjecture in a slightly different way, that can be this problem for the generation of kids now. Why do I say this? The radical is actually a really simple idea. And I realized that I had to compute radicals in elementary school. They just didn't call them radicals. And if we look at the ABC conjecture of Oesterle and Masser, they conjecture that if A, B, and C are relatively prime integers, such that A plus B equals C, then for any epsilon greater than 0, there are only finitely many exceptions to the equation C is less than the radical of A times B times C raised to the power 1 plus epsilon. But you don't need to tell people about all this epsilon business. Why do I say that? In this paper, we don't deal with any epsilon. We've made this much easier. We restrict ourselves to the scenario epsilon equals 1. And you can still do all sorts of things with that. It's still an open problem. And so you can restate the ABC conjecture with epsilon equal 1, and it's suddenly a very simple statement. If A, B, and C are relatively prime integers, such that A plus B equals C, then there are only finitely many exceptions to the equation C is less than the radical of A times B times C squared. And I think that is a statement you can easily say to any high schooler. So the title of the talk, the ABC conjecture implies that only finitely many Cullen numbers are rep units. I have now told you what a Cullen number is, what a rep unit is, and we have stated the ABC conjecture. So here is our theorem. Surprise, we're actually proving something stronger than the title. We're saying that we're proving that the ABC conjecture with epsilon equal to 1 implies that for any fixed s, when s is greater than or equal to 2, there are only finitely many s-Cullen numbers, C sub s comma n, that are rep units. And I told you I was going to give you guys 2 primes. Rep units have length 3 or greater. We're going to have one proof showing that there are only finitely many s-Cullen numbers that are rep units of length 3. And we're going to have a separate proof showing that there are only finitely many s-Cullen numbers of length greater than 3. So we're going to move on to our proofs. First, s-Cullen numbers that are rep units of length 3. Let's start out by writing the definition of a s-Cullen number and the definition of a rep unit of length 3. We set them equal to each other. Notice they each have a plus 1 on the end, so we can just remove that. And that gives us n times s to the n is equal to b times b plus 1. Well, the ABC conjecture with epsilon equal to 1 says that for all but finitely many b plus 1 is less than the radical of, let's break down b plus 1. It's b plus 1. So if we take b plus 1 times b times 1, we can apply the ABC conjecture. So b plus 1 is less than the radical of b times b plus 1 squared. And we just said that b times b plus 1 was the same thing as n times s to the n. So we plug that in, and the radical of n times s to the n is certainly less than s times n. So we get this nice equation. So n times s to the n is equal to b times b plus 1, but that's less than b plus 1 squared. And we said that b plus 1 was less than n times s, so we can take that to the fourth and distribute. We can take logs, rearrange a bit, and we get that this polynomial is less than a logarithm. We know that can only happen for finitely many values of n. So there we go. It's proven, right? We have finitely many exceptions depending on b. We have finitely many exceptions for the values of n with this polynomial less than this log. So it's proved. So now let's move on to s-Cullen numbers that are rep units of length greater than 3. And I'm not going to go through all the details. I'm just going to show you how we use the same trick. So we again take an s-Cullen number and we write it as a rep unit of length greater than 3 for some base b. And they both end in a +1, so we can subtract the 1 from each side and we can factor out the b. So we have n times s to the n is b times another rep unit base b. So we can rewrite that as b to the q minus 1 all divided by b minus 1. And we can multiply both sides by b minus 1. And notice that the right-hand side is b times b to the q minus 1 minus 1. Well, whenever we have a power plus or minus some small number that is begging, or especially plus or minus 1, that is begging for us to apply the ABC conjecture. So here we have b to the q minus 1 minus 1. If we have b to the q minus 1 is less than the radical of b to the q minus 1 is b to the q minus 1 minus 1 plus 1. So the radical of b to the q times b to the q minus 1 times 1 is going to be less than or equal to this radical here. And we know that this is going to hold for all but finitely many BQ pairs. So if this holds, which we know holds for all but finitely many BQ pairs, then we can rewrite the right-hand side because b times b to the q minus 1 is the same thing as b minus 1 times n s to the n. And the radical of b minus 1 n s to the n is bounded above by s times n times b minus 1. We can distribute the square. And notice that if it's greater than b to the q minus 1, it's certainly greater than b to the q minus 1 minus 1. But if we divide both sides by b minus 1 and multiply by b, our left-hand side suddenly looks very familiar. If we add 1 to the left-hand side, the inequality is preserved if we add the much larger number, s squared n squared b, to the right-hand side, which gives us this inequality. And this left-hand side can be rewritten as n s to the n. Well, guess what? We can divide both sides by n. We can divide both sides by s squared. We get s to the n minus 2 is less than nb squared. And then you have a little more fun with bounds, take logs, and you get our result. So those are our theorems proven. But let's look at some concrete examples. And so if you look at the sequence C, S, comma 2, keep in mind our theorem was for fixed S. What if we fix n and let s vary? So if you look at the s-Cullen numbers of length, if you look at 2 times s squared plus 1, sorry, that sequence, if it's a rep unit of length 3, let's write that out. 2s squared plus 1 is a rep unit of length 3. If you divide both sides by, if you subtract 1 and divide both sides by 2, you suddenly see that s squared is both a square and a triangular number. And Euler already figured out which numbers are square triangular numbers. So that gives us an infinite family of these s-Cullen numbers, which are length 3 rep units. We are also able to rule out one potential family of s-Cullen numbers, show that they can't be rep units by looking at elliptic curves. And we also did explicit computations. There are no s-Cullen numbers, which are also rep units where s is less than or equal to 75 and n is less than or equal to 75. Or if you want to increase S and decrease N, there are no s-Cullen numbers with S less than or equal to 10 to the 6th and N less than or equal to 10. If you want to check our code, this is where it lives. And if you want to check out the paper, here is where it lives on the archive.
Thank you.